Now, what if we have this example? We've got fxy is square root of 1 plus x cubed, I, plus 2xyj. And C is going to be the counterclockwise triangle with these vertices 0, 0, 1, 0, and 1, 3. And you need to find out what that line integral is. Well, let's try drawing this thing. It's always a good idea to try drawing what our scenario is so we can maybe get a better idea about what this thing looks like. So what is that? That's 1, that's 0, 0, 1, 0, and 1, 3 is going to be somewhere up here. So here's the triangle in question. We're looking at something that's got these vertices and is counterclockwise oriented. I'm going to try to draw this like a triangle. So what can we say? Well, can we remove an integral? We can only remove an integral if the gradient, we can only remove an integral if qx is equal to py. Well, qx is 2y, but py is 0. So that's not an option for us. That's okay. Let's try adding one. If you want to add one, well, that's where you have to hit this with Green's theorem, where you can say this is the integral over C of f dot dr. That's the same thing as the double integral over d of qx minus py dA. Now, in this case, we know what qx minus py is. We found, and by the way, we can do this because our curve C encloses this triangle. So we can do this. Now, qx minus py, what's that going to be? Qx minus py, we already know that. That's just 2y, because we found what qx and py are. And what about D? Our region D, now this is the point 3, this is the point 0. So you can think about this as all points x and y, so that y is between 0 and 3. You can see that this makes most sense as what we had been referring to as a type 2 region. And on the one hand, this one of these, this is going to be the curve x equals y, right? I'm sorry, I'm looking at this thing and I'm realizing that I went from 0, 0 to 3, 3. This is insane. What kind of a cruddy picture is that? I'm clearly not thinking. Let me try this again. 0, 0 to 1, 0, 1, 0 to 1, 3, 1, 3 to 0, 0. That's better. Now you can still do it this way, but I'm gonna do it differently. So I'm going to instead do this as a type 1 region, because you have to deal with fewer fractions that way. X is going from 0 to 1, and y is going from 0 to 3x. There we go. That's what I wanted to say. And that gives us this region inside of there. So the integral over f dot dr, what's that going to become? That is the integral from, or that's the double integral over this triangle of the function 2y dA. In other words, the integral from 0 to 1 of the integral from 0 to 3x 2y dy dx. And this is fairly straightforward. This is the integral from 0 to 1 of y squared evaluated at 3x, or in other words, 9x squared dx. Or in other words, 3. That's it. So Green's theorem was very helpful here. Now, can you do this problem in can you do this problem directly? I honestly don't know. I really don't know if you can. The problem, you see, is when you get to that diagonal bit, you're going to have to deal with 1 plus x cubed. Pardon me. You have to deal with 1 plus x cubed. And when you deal with 1 plus x cubed, that's going to be a really, really challenging, maybe even impossible integral to work out. So that's no good. Questions so far? Okay. Now, here's another problem. What if you have fxy is, that should be fxyz. It's a typo. And S is this hemisphere. And we want to evaluate, evaluate the surface vector field integral. Again, there are always 3 different approaches. We can try adding, removing, adding an integral, removing an integral, or doing it directly. Now, if we wanted to add an integral, that's if S encloses a solid region E, and if it does, we get the integral, we get that that's going to become the double integral over that surface of f dot ds is the triple integral over that region of the divergence of f. If S encloses a solid, but does it? S is the hemisphere, right? It's this part of a bowl, or I guess a sideways bowl in this case. So it's not enclosing anything. So that's not an option for us. So maybe we can remove one. Can we? Well, that would be that would be Stokes' theorem. For some other vector field G dot dr, if the curl of G is equal to F. But that's hard. It's hard finding a vector field that's the anti-curl. So that might not work either. Besides, you can only do that if the vector field you're working with is in fact the curl, and if it is in fact the curl, then the divergence would be 0, and the divergence isn't 0 in this case. It's z minus 2. So you can't do those things. We have to do it directly. And again, you can ask yourself, okay, well, what's the formula? F dot ds, principles of integration. We're doing a double integral. It's over a surface, which has area, which is 2-dimensional. So we're going to do a double integral of f of your parameterization. Your parameterization of how many variables? 2 dimensions, 2 variables. du, dv, that's a vector. We have to dot it with another vector. What do we dot it with? We dot it with something that's some kind of derivative of the parameterization. The only thing we can do that in a reasonable way with is RU cross RV. The only thing that's left is to find out what that parameterization is. Now for a sphere, that's fairly spherical coordinates. We can say x, in this case, is going to be, x is going to usually write rho cosine theta sine phi. Y is rho sine theta sine phi. And z is rho cosine phi. But in this case, since the radius is 2, we can see that, and that from the definition of the sphere that we've been given, we know that rho is going to be 2. So actually what we want is x equals 2 cosine theta sine phi, y equals 2 sine theta sine phi, and z equals 2 cosine phi. Let me get rid of some of the stuff up here. So, and that's how we know now that's a standard parameterization for a sphere, and it's a parameterization that, that everyone should be familiar with as we're doing spherical coordinates and things like that. And it's really going to come in handy. So make sure that that's something you're comfortable recognizing when spherical coordinates are a good idea. So we calculate the cross product, r phi cross r theta. Oops, sorry. R phi in this case, 2 cosine theta cosine phi, 2 sine theta cosine phi, negative 2 sine phi, negative 2 sine theta sine phi, 2 cosine theta sine phi, 0. So we take that cross product, and what do we find? We find that that's going to become, become 2 cosine theta sine squared of phi in the I direction. In the j direction, we're going to get plus, I said 2, but actually I meant 4. Plus 4 sine theta sine squared phi in the j direction, plus, and then I'm going to skip a little bit, but this is going to become 4 cosine phi sine phi. Now the question is this the parameterization we want? Well, that's the same thing as sine phi times r of phi theta in the first place. Now remember, by the way, that what are our values of phi and theta? Well, theta, now y is positive, and if y is positive, that means that theta has to be going from 0 to pi. Phi, on the other hand, since it's coming all the way down from the North Pole to the South Pole, only just one hemisphere, phi is going to go from 0 to pi as well. So sine phi is a positive number. So the normal vector, because remember this, this cross product is in fact the normal vector. So the normal vector is in the same direction as the position vector. And if you imagine what that would look like, we've got the normal vector is going in the same direction of the position vector in this hemisphere. What does that mean, though? Well, it means that if here's our hemisphere, there's the hemisphere, and you're starting off on the inside with your vector. Well, the normal vector in that case is going in the same direction, right? But we're told that our surface is oriented inwards, which means we want to actually be opposite that. That's okay, that's not a problem. You can do that. You can make it oriented inwards just by flipping it. So the orientation is off. But that's an easy fix. We're going to use r theta cross r phi instead to reverse the orientation, and that's going to give us -4 cosine theta sine squared phi I minus 4 sine theta sine squared phi j minus 4 cosine phi sine phi. All right, so that's great. Now, we now need to actually calculate this thing. Well, to do that, we're going to need to find what f of r of phi theta actually is. Look at that for a second. What we find is that's going to become 16 cosine theta sine cubed phi cosine phi. That's x times z in the I direction, plus 8 sine theta. I'm sorry, I'm plugging in. I'm plugging in the wrong values. I'm plugging in the cross product, not the actual value of the equation. Oops, my mistake. So f of r phi theta. Okay, plugging in what I meant to plug in, because in this case x is 2 cosine theta sine phi. Z is 2 cosine phi I minus 2 sine theta sine phi j. Oh, sorry, minus 4, excuse me. Plus 4 cosine theta, oops, plus 2. Man, I'm on a roll today. 2 cosine theta sine phi. Okay. All right, so let me make sure that I'm getting all of this right. I'm going to erase the top piece of what I have, but only the top piece, so that I can keep track of what's below. Okay, so f of, now you're actually going to take the dot product in this case, f of r of phi theta, dotted with r theta cross r phi. And what's that going to become? You take that cross product, and it's going to become -16 cosine squared theta sine cubed phi cosine phi. I think I did all that correctly. Plus 16 sine squared theta. Oh, sorry. Sine squared theta sine cubed phi. Minus 8 cosine squared, oh, sorry, not squared, cosine theta cosine phi sine squared phi. Bit of a mess, let's try cleaning it up. We can bring out a sine squared phi negative 16 cosine squared theta cosine phi sine phi. Can we clean this up at all? Plus 16 sine squared, sine squared theta sine phi minus 8 cosine phi, cosine theta cosine phi. And I don't think we can really clean that up a whole lot more, unfortunately. So that's about the best we can do. So we calculate this thing, f dot d s. And in the interest of time, I'm not going to actually go and do the entire calculation, but you'll find it in the lecture notes once I post these to Canvas, which should be this afternoon. Once you actually do this whole thing, you've taken the dot product, you've gone through this whole process. Actually, let me make it a little bit nicer. Let me write this as 8 sine squared phi of negative 2 cosine squared theta cosine phi sine phi plus 8 sine squared theta sine phi. Oh, sorry, not 8, 2. Oops. Minus cosine theta cosine phi. And again, I'm not going to go through the whole d phi d theta. And again, I'm not going to go through the whole derivation right now. A lot of it, a lot of stuff actually, you know what? I take it back. I will go through the whole derivation because a lot of this is gonna go away now that I'm staring at this for a little bit. The well, some of it will go away. Actually, not as much as I thought it would. Okay. Yeah. Well, looking at this for a little bit, we can. It'll turn out that integral from 0 to pi, integral from 0 to pi, negative 16 cosine squared theta cosine phi sine cubed phi d theta. That's going to go away because that's going to become sine to the 4th phi evaluated from 0 to pi, which is 0, plus 0 to pi, 16 sine squared theta sine cubed phi d theta. That might not go away, but that'll still be not terrible. And we'll fix that in a little bit. Minus integral of 0 to pi, 8 cosine theta cosine phi sine squared phi d theta, and that is going to go away. So the whole thing we're left with at the end of the day is integral from 0 to pi, 16 sine squared theta sine cubed phi d theta. And it's actually not terrible to work out what that has to be. Integral from 0 to pi of 8 times, using our trig identities, 8 minus 1 minus cosine 2 theta, d theta, integral from 0 to pi of, in this case, this is sine phi times 1 minus, 1 minus cosine squared phi d phi And what's going to happen here in this case is the first of these integrals, this guy is just equal to 8 pi. Sine phi is going to go away. So the whole thing that we're left with is 8 pi times cosine cubed phi, evaluated from 0 to pi, which becomes negative 16 pi. I believe that's the end of that calculation. So it's a little, it's a little lengthy, but again, not terrible. Not terrible if you just really keep be careful and conscientious about what the integrals are. And once you get used to this a little bit, you can see that a lot of these trig integrals are going to vanish once you actually go off and calculate them. Okay. So let's do a couple more. So now here we have the, again, that should be fxyz. I'll have to fix that when I upload the notes. X squared z plus xy squared plus z squared. C is the curve of intersection of this plane and this cylinder. Evaluate this line integral. Again, we have three options. We can add, remove, or do directly. Now, if we were to try to, now can we add an integral? Well, if we try to get a sense of what this scenario looks like, what do we have? What we get is something that looks like this. Right? We've got it's some kind of plane. This is emphatically not to scale. In fact, so much is it not to scale that I should actually probably just fix that entire picture. But basically, it's going to look something like this. And let me try that again, actually, because that's laughably not to scale. The problem is that this x plus y plus z equals 1. So actually, it's going to look something like this. You've got your and oh wait, crap! I was right. Anyway, no, I've screwed the whole thing up. Okay, never mind. Point is, oh geez. Okay, point is, this curve is the important observation here is that this curve C is the boundary of a plane. Strictly speaking, a slanted disk. So if we're going to try adding an integral, we can do that because that's Stokes' theorem. F dot dr is the double integral over the disk of the curl of F. So let's try calculating the curl. Del del x, del del y, del z, x squared z, xy squared, z squared. And you actually calculate this thing, and what we find, this comes out to be, in the I direction, it's going to be 0. In the j direction, it's going to be x squared. And in the k direction, it's going to be y squared. Well, that seems like a nicer integral to work with in this case, a nicer curl. And what about the, or a nicer vector field? The surface in question, we can think about this as x equals x, y equals y, and z equals 1 minus x minus y, because it's a graph of something. In this case, our standard formula for this cross product is going to come out to I plus j plus k. And I'll let you work out the details there about why that works out that way, but it does work out that way, which is exactly what we want and exactly what we expect. And it's excellent news for us, because what that means is that the dot product of the curl and our normal vector is x squared plus y squared. So what Stokes' theorem tells us in this case is this is the double integral over this region D, x squared, not region D, I'm sorry, surface S. No, I did mean region D, I'm sorry. X squared plus y squared dA over that parameterization. And I think the best thing to do here is to hit that with polar coordinates. And what that's going to be is the integral from 0 to 2 pi, integral from 0 to 3, because the radius is going from 0 to 3, because we're told that the cylinder has a radius of 3. R cubed dr d theta, which comes out to pi over 2 times 3 to the 4th. Or in other words, 81 pi over 2, after you calculate that. Stokes' theorem made this problem significantly easier. And we can take advantage of that strictly because our curve is a closed curve. It encloses some kind of nice surface, and we're told exactly what that surface is. That surface is just going to be this disk. We've been told it's this disk, and Stokes' theorem is the way to go for something like this, because we know that it's a closed curve. Okay. On the other hand, we can go the opposite direction as well. So if we're told that it's the curl, if we're told that we're integrating the curl, we may consider trying to hit that with Stokes' theorem coming out of the gate, f dot d r. Now, what is C? C is the part, or sorry, the boundary rather, of the part of the sphere. And what that really means is it's going to be a circle, right? With z equals 1, and if z equals 1, that means that x squared plus y squared is equal to 4. So we've got a couple different options here. We can try one of two different things. Here's the first thing we can try. That's a relatively easy thing to parameterize as a curve. That's going to be 2 cosine t I plus 2 sine t j plus k, which means that r prime of t in this case is going to be negative 2 sine t I plus 2 cosine t j, and the k term is going to go away because it's constant, and you just differentiated a constant. Meanwhile, f of r of t, what's f of r of t? 4 times 2, so that's going to be 8 cosine squared t. Did I do that right? Yeah, I did. 8 cosine squared t sine t I plus 4 sine squared t j plus e to the 4 sine t cosine t k. Why did I not include a z term? Because the z term is 1. But in fact, it didn't matter what the z term was, because once you take this dot product, it's going to go away anyways. This becomes negative 16 cosine squared t sine squared t plus 16 sine squared t cosine t. Now that's not terrible, but it's not really great either. It doesn't really give us what we want. And if you try calculating that, 0 to 2 pi, should it be 16? No, it should be 8. That should have been an 8 over there, not a 16. And if you try calculating that, that's going to be 8 sine squared t cosine t minus 16 cosine squared t sine squared t dt. Not terrible, not great. So maybe that's not what we want to try to do. Let's try something else. Because there's another thing we can use in this case. What if we instead use a different surface? And that surface is going to be the plane z equals 1. With x squared plus y squared less than or equal to 4. Because what Stokes' theorem really tells us is that the double integral over S of the curl of this thing is the same thing as the double integral over the curl of this other surface, and possibly a better one. Let's see what happens in that case. Let me try clearing out some of this stuff. So we're going to use, in this case, S prime is the plane z equals 1, where x squared, plus y squared is less than or equal to 4. What is the curl of f anyways? The curl of f, del x, del y, del z, x squared y squared, excuse me. So y squared, and we get, in the last coordinate, z cubed e to the x, y. IJK. And you take this curl, and what do you get? Well, in the I coordinate, this is going to become xz cubed e to the x, y, I, minus y, sorry, hold on a second, minus yz cubed e to the x, y, j, minus x squared. Okay. So now that we've done this, what we can say in this case, now we know that the surface has the parameterization x equals x, y equals y, z equals 1. So in this case, the cross product, Rx cross Ry, it's just going to be k in this case. So because it's just k, because that's the only thing that survives after doing all of this, what that means for us is the curl of f dotted with this new normal vector, Rx cross Ry, that's just negative x squared. So the double integral of the curl of f, that's just going to become the double integral over this respective region, negative x squared negative x squared, oriented inwards. I'm sorry, that should have been oriented upwards. I forgot to change that. I'll fix that when I actually do the thing. Negative x squared dA. Probably the best thing here is to do this in polar coordinates. That becomes integral from 0 to 2 pi, integral from 0 to 2 of negative r cubed cosine squared theta dr d theta. R cubed, that's going to become 1/4 times 2 to the 4th, or in other words, 1/4 of 16, or in other words, 4. So negative 4, integral 0 to 2 pi of, again, best thing to do here is to hit it with your trig identity, 1 plus cosine 2 theta d theta, which in this case is just going to make this whole thing out to be negative 4 pi when all is said and done. That's what this thing comes out to. Because the cosine 2 theta term is going to go away. And that ended up being an easier integral than the line integral. So you can, so whenever you're using Stokes' theorem to calculate the double integral of a curl over a surface, you can either bring it down to the surface and just, bring it down to the boundary, the curve, and take the line integral over the boundary curve, or you can try calculating a different surface integral for a better surface. Both of these are valid strategies. Okay. I want to do one more example. And here we have x cubed plus y cubed plus z cubed. X cubed I plus y cubed j plus z cubed k is our surface, as our vector field. S is the surface of the solid bounded by this cylinder, x squared plus y squared is 1, and the planes z equals 0 and z equals 2 oriented outwards. Again, whenever you see anything that says surface of the solid, that should scream to you divergence theorem. So we want to use the divergence theorem in this case. Now, can you do this directly? Sure, you can. Is it a good idea? Maybe not. Because you're going to have to be able to do this with 3 different pieces because the surface has 3 different sides to it. So the direct approach has 3 sides. The removing an integral with Stokes' theorem ordinarily, you can do something like this, but the problem is twofold. First of all, f might not be a curl. And in fact, it isn't. And the boundary curve might not exist. And in fact, it doesn't. Because it's the surface of a boundary. Excuse me, let me try that again. It's the surface of the solid. And that surface has no boundary to it to begin with. There's no edge. There's no edge to the surface. So the only option we have left as far as strategies is to add an integral using the fundamental theorem of line, fundamental theorem of line integrals. God, I can't speak or write today. Using the divergence theorem. Now the divergence of our vector field is quite nice in this case. It works out to be 3x squared plus 3y squared plus 3z squared, or in other words, 3 times x squared plus y squared plus z squared. And our solid, probably the best thing here is to write this in cylindrical coordinates. After all, it's basically a solid can. In r theta z, this is going to be all r is between 0 and 1. Theta is between 0, theta is between 0 and 2 pi. And z is between 0 and 2. Outward oriented, not a problem. And this comes out to the triple integral over e, 3x squared plus y squared plus z squared dv, integral from 0 to 2 pi, integral from 0 to 1, integral from 0 to 2, 3r times r squared plus z squared dz dr d theta. Let me clear some space up top to make this a little bit easier to actually work out. Now, there are no theta terms, so you can actually, and since there are no theta terms, you can use our little separation trick to just write out 2 pi times the whole thing to begin with. 0 to 1, integral 0 to 2 of 3r cubed dz dr plus 2 pi integral 0 to 1 integral 0 to 2. Actually, I'm going to write it this way, integral 0 to 1, 3r cubed, 3r, dr, integral 0 to 2, z squared, dz. This becomes the integral 2 pi times 2 for the z times 3/4 on the first bit plus 2 pi times 3/2 the second bit times 4/3, which is what you get when you take, 4? No, I'm sorry, 8/3. Because it becomes z cubed in that case. So in other words, that's 3 pi plus 8 pi, or 11 pi. That's our final answer in this case. Now, again, can you do this directly? Yeah, you can. It's just not really recommended because you've got 3 surfaces that are all part of the same surface, and because it's piecewise defined in that way, and it's just you're really gonna cause yourself a headache if you do that. So the best solution, I think, is to use the divergence theorem here because it's a solid object. But if you want to play around with how you do it directly, then be my guest. Are there any final questions of anything that we've looked at today, or over the course of the semester even? And if there aren't, then I'll say it's been a pleasure. Thank you very much, and good luck on the final. Take care, everyone.